Okay, now we are recording. Welcome everyone to another Friday, like the quantum hardware course. And today we continue. I mean, we stop. We finish like the part of the coherent states that was like we make like a brief review about coherent states that will be useful during the when we are doing quantum computation. So today I'm planning like to talk a little bit about the things we'll do now, and we'll get into details specifically about phase shifters. It's a type of material that is used in optical models a lot. So I will start sharing my screen. And again, I'll follow the same. Like I will show some slides before just to introduce, and we go to the whiteboard. So okay. So this is the again I'm using like the Nielsen Schwenk book, and today we'll use more than the other time that for the part of the coherent states was not so details here. So we use another books to to have the this presentation about the coherent states. So let's first just review a little bit about coherent states, the main properties that we saw. We saw in the last lectures that one scheme for generating single photons in the laboratory is attenuating the output of a laser. And in this lecture, we will apply some of this previous knowledge and start to discuss some devices important to quantum hardware computation, as for instance, phase shifters that I will get into details today, beam splitters, and nonlinear optical slabs. So today I'll talk more about phase shifters, and the next Friday, beam splitters. Maybe I'll need 2 Fridays to talk about beam splitters, and then we go to nonlinear optical models where we will like mix everything and try like to do quantum computation. So this just to review about coherent states. So we saw that a laser outputs a state known as coherent state. We call like this eigenstate alpha, that can be given in terms of the number state or Fock state n in this way. A relation like this. That we prove this, and this is the equation 716 in the Nielsen Schwenk book. Okay. So where this n is the n photon energy eigenstate. And we also prove that the mean energy is proportional to alpha square, where alpha is just a complex number. And when attenuating, in fact, alpha is the eigenvalue of the amplitude operator. Right? That's the A that sometimes we call like the aniquilator operation. I forget to put here. A applied to alpha give me to the eigenstate alpha, give me the eigenvalue alpha in this way. So when attenuated, a coherent state just becomes a weaker state, and a weakened coherent state can be made to have just few photons. So some properties about the coherent states that we saw that it has a Poisson distribution. We showed this in the last Friday, and this the picture I tried to draw to you guys in the whiteboard. So this is the picture. It's in the Scully Zuberi book. So here is basically, in this case, A here, it use like alpha 0.1, alpha square 0.1. So this first line here, this here. So we see that we have a peak around 0.1, around 0. And we go keep like increasing for alpha square equal to 1. This means this plot here. So the peak is close to 1. And the other, the case C, is this plot here, where the peak is around 10, because we use like alpha square equal to 10. So then this alpha square is that you show is the average in the number of the particles. Okay. Okay, so this is one property. Another property, very important, that's the coherent state at the minimum uncertainty state. The quantum state with the minimum uncertainty state. This one. Let the coherent state to be one of the closely to the classical state, right? And this has some advantage experimentally because of these properties, it's much easier to produce it in the laboratory. It has a completeness relation that in this case is given by this expression. And the wave function that corresponds most closely to the classical field with this minimum uncertainty packet displaced, in this case here is displaced by an amount that I just call Q in the positive R direction is given by this. So this is the wave function associated with the coherent state. And just a comment, we note that it also, because you see that it's something like when R goes to plus or minus infinity, it goes to 0, and it has a peak around Q, right? So this function like this. That's similar to this. And we note that it oscillates back and forth in the single harmonic oscillator potential without changing its shape. It's always this shape. It means that it sticks together or coheres. And this is because of this, we have the name to this type of states. So this is the wave function. It's always this. Okay, and just one example. If we use like equation 716 that we proved in the beginning, this equation, and let's consider alpha square equal to 0.1. So this means that the source has a rate of 0.1 photons per unit time. So using 716, we can find this. Just like put where we have alpha square here in this equation, we put 0.1. If you do that, you'll have something like this, a series like this. And we can note here that about 90% of the time, no photons, that is this state, comes through, right, for alpha in this way. So we can use a technique called parametric down conversion to read out the photons. And this will involve sending photons of frequency omega 0 into a nonlinear optical medium that we will describe during the next lectures. And these will generate photon pairs with these frequencies and wave numbers associated. So when a single omega 2 photon is detected, then a single photon omega 1 is known to exist. By coupling this to a gate, which is open only when a single photon, as opposed to 2 or more, is detected. So basically what he's saying here is this. We have the laser. You send a nonlinear crystal type that will still study the quantum properties of this type of material, and using this technique, parametric down conversion, we can generate photons with frequencies omega-1 and omega-2. So single photons can be detected with a high quantum efficiency for a wide range of wavelength using a variety of technologies. And the most important characteristics of a detector is its capability of determining with high probability whether 0 or 1 photon exists in particular spatial modes. So the type of material that you will be using to make this type of detection in practice is related with this one. So in practice, imperfection reduces the probability of being able to detect a single photon. And the quantum efficiency, it's between 0 and 1. Is the probability that a single photon incident on a detector generates a pair like this. And the most experimentally accessible devices for manipulating photon states are basically these ones: mirrors, phase shifters, beam splitters, and nonlinear optical devices. And we'll see in details like the quantum properties in the next sections, lectures, basically these three here. Okay, about mirrors, just some comments. Mirrors, they are high reflectivity mirrors would reflect photons and change the propagation direction in space. And mirrors with about 0.01% are not unusual. It's very common. And we will take these for granted in our scenario. Okay, but in terms of mirrors, we will not see too much details. We'll see more today, like phase shifters. And in the next Friday, or probably 2 Fridays, we study some quantum properties of beam splitters. So, okay, so we'll see now the whiteboard, where we will discuss some important properties of these devices, especially today, the phase shifters, and turn to the quantum description of them with application of quantum computation. In particular, in this type of representation, dual Breuil representation, where here, just to remind, 0 is the state, no photon state, and 1 is the state with one single photon. And we use this correspondence that we associate the state 0, 1 with the logical 0, and the state 1, 0 to the logical 1. Okay, but we will see this in the end. Just to remember, because I think 3 weeks ago we commented this. Like, here's just to refresh our mind. So, okay, questions, comments?
Yes, I have a general question. If there's a relatively quick answer, does the quantum prediction for the coherent state differ from the classical prediction, in that the coherent state with large n is an approximation to the classical description?
Actually, it will be very similar because it's close. I mean, the coherent state is close as possible as the classical state.
Thank
So
you.
I don't know a number exactly, but will be because it's simple to produce in the lab. I mean, one state with the quantum
Yeah.
property that is simple to produce in the lab. So I think will be similar. We have no big discrepancy. But I don't have a number to say to me. I really.
I agree with saying mass for sufficiently large n.
Yeah, I think is about the same. Be about the same. Like that example that we use, like about 90% of the time we see no photons for an average number of particles of that, and Z.1, I think. So I think would be similar. Okay.
Yeah, thank you.
Okay, welcome.
So this kind of gives me a line to connect the quantum math to the physics. It's a little harder in other places, make it.
Yeah, okay. So let's see some quantum computation. So here, just some more few comments. Like, we know that arbitrary unitary transforms can be applied to quantum information. Encoded with single photons in the dual rail representation. So, just to repeat what was in the slides, C0, 0, 1, plus C1, 0. So arbitrary unitary transforms can be applied to quantum information encoded with single photons. The dual rail representation using, that's the representation, using phase shifters, beam splitters, and nonlinear optical Kerr media. We'll see this in the future. What is this? Today we will focus, as I told you, on phase shifters. So, but in general, this works by giving a quantum mechanical Hamiltonian description of each of these devices. Okay? Okay, and we also know that the time evolution of a cavity mode of electromagnetic electromagnetic radiation is modeled quantum mechanically with the help of a harmonic oscillator. Okay, so just to remind things. So remember that 0 is the ground state or the vacuum state, the cat 0 state. And 1, that is given in terms of 0 in this way. This is a single photon state. And in general, we have n, a Zaga, applied to the vacuum. Okay, this is the n photon state. And a dagger here, and a dagger is the creation operation. Creation operator. For this mode, no? For the mode. Okay, in free space, the evolution is described by the Hamiltonian. That in general is this. H bar omega adaga. Okay, well, this guy here is the number operator. Okay, so in free space, we have from equation, applying equation 713. Just to remember, 713 in the New Shuang book, okay? So is this equation, psi of t is equal to time evolution. Linear equation. I h t h bar psi 0. And using psi 0, I think this 0 plus 1. The time evolution is psi of t exponential minus I h t h bar. Applied to psi 0, but let's say psi 0 is this. Is a state in superposition. So if you use this Hamiltonian here, we find exponential minus I h bar goes away, omega t a applied to this race. Okay, and here we could like expand the exponential operator, and we would find this minus I omega t a dagger a plus the other terms of the expansion applied to this. Okay, and this would just give this first part. This is the identity. So we'll give C00 plus C11 minus I omega t. And this goes here. Omega A. Let's write this like C0, right, is a constant. Omega A 0 plus C1 and omega A1 plus the other terms. And we could see here that since I have here the annihilator operator applied to the vacuum state, this would be 0. So this is C00 plus C11 minus I omega t. And this guy here is C1. And here's when the vacuum state applied to 1, I will have the first excited state. I will have the annihilator operator applied to 1 will give me the 0 state. And when I apply the a dagger, the creating operator to the 0 state, this will give me 1 again. So this is different of 0 and will give just the 1 plus the other terms. And the other will be valid for the same thing, will be valid for the other terms. So we will have like C0 half C00, this plus 1 minus I omega t plus other terms 1. You can check this. If I have this square, I would apply like the square to the two photons state. And if I have the next term here would be something like this. 2. But again, this would give me like 1, and this will give me 2, and the same. Okay. So in general, oh, sorry, this is 1. It's not 2. The next term here would be, we would have something like this. 0. This would give 0, and this give 1. And the same for the other terms. Like when I have 3, when I expand the exponential, would have like the to the cube term will always be. When applied to the vacuum, we always give 0 as a result. And when I applied to the one single photon state, this would always give me the one single photon state. So we have an expression like this. And this could be written as C0, 0, plus or minus I omega t 1. Okay? So this is the time evolution psi of t for that Hamiltonian. So this is the free space. So our goal is to do something similar to the phase shifters today, and then something similar to beam splitters in the next Friday. So let's put your phase shifters. Question?
So in the chat, Constantine asked, where is, can't make that out, CT?
Your audio is not so good today, George. I think it's better I read.
If you can see it.
Let me. Where is C1? Oh, it should be here. If it's not, this was my mistake. Okay, C1, yeah. Yeah, let's see if I mistake here or if in my notes. No. See, it should be here. You are right. C1's here, C1's here, and here disappears. Thanks. Where's Constantine, right? Thanks, Constantine. C1. Okay. So, okay, so we'll do something similar to materials like phase shifters today and beam splitters in the next. So in general, let's give some like classical properties of phase shifters. They are slabs of transparent medium with index of refraction eta, which is different from eta 0, where eta 0 is the index of refraction of free space. Okay. One example Nielsen Schwenk gives for a phase shifter is what he called borosilicate glass. It has an index of refraction which is about 1.5 to 0. These at optical wavelength, of course. So just to like for curiosity, like I was looking exactly what is this, like to have a visual. What's a borosilicate glass? And was just some minutes before the Wikipedia has some example here. It's like very usual glass like this that is used. This is, I think, this is used to guitar slide, but it has some other examples here, like this one in chemical things. This one for cookies. And I was looking for the index of refraction to see if it's the same that the book is saying. Is there's something 1.5 here. Okay, but this is just to see exactly what is this. There are some other examples that he gives here. A lot of applications, but we are interested in like the quantum properties, right? So let's return. Okay, so this type of material works as a phase shifter, and still some classical properties like the propagation in general. But in general, propagation in a medium through a distance L changes a photon phase by exponential AI L, where K is the index of refraction in the middle, the eta, omega C0, where C0 is the speed of light in the vacuum. Speed of light. Okay. So a photon propagating through a phase shifter will experience a shift of this. So exponential, what I'm calling here delta eta L omega over C0, where this could be written. This delta eta is eta minus eta 0 L omega C0. Okay. So does a photon from a phase shifter will experience a shift of this type compared to a photon going the same distance through phase space. So we have this shift here, the index of refraction. Okay, so this is the classical. The thing now is how we could like describe this quantically. What we need to use to describe quantically these properties that people like measure in the laboratory, for instance. So let's change the color. Quantum description. So okay. So a phase shifter operator. Let's call it P. I'm using the notation of the Nielsen-Schwenk book, so that's why I'm using P. P for phase shifter. But don't be confused. P we use also for probabilities, right? Or momentum. So I think it's not a good choice, but because I want like to follow the notation, so I'll use P instead. So a phase shift operator X, you'll see, for instance, like for beam splitters, the operator will be B. So P for phase shifters, B for beam splitters. Okay. So this P acts just time evolution. But at a different rate. And localized to localized to only modes going through it. In general, we see that P is given to exponential minus E delta N, where N is the number operator. Okay, the quantum mechanical description. Okay, and this is because light slows down in a medium. With larger medium of refraction. Yeah? But at eta bigger than eta 0. Okay, so in the vacuum, in general, specifically, it takes in the vacuum a time to propagate a distance L. But in the medium, and this time is just like L divided by C0, right? And in the medium, light will experience let's say difference, let's call delta, that's equal eta to the eta 0 L omega C0 would experience a difference to propagate, would experience a difference delta to propagate a distance L. In the medium with index of refraction eta. Okay, we'll have this difference here. So it's basically the same thing we did before. Let's see one example. The action of P, my operator P, of phase shifters on the vacuum is to do nothing. Okay? Since we define P exponential minus E delta eta, N, sorry, exponential minus E delta like this, A dagger A. That's the definition of the N operator. So if we apply it to the vacuum, we already know P to the vacuum is this exponential A to the vacuum make the expansion, plus the other terms, and this will give 0. Right? This applied 0 applied to A gives 0, and applied to the identity is just the eigenstate 0. And for P equal to 1, sorry, for the eigenstate 1, P, we already saw this before. It's just this expansion, dagger A, plus the other terms, applied to 1. This will be just exponential minus I delta 1. Okay? So this is how, so P, the phase shifter do nothing in the vacuum state. And once you are in the middle, like in this operator in the vacuum state do nothing. And once you are in the middle, has the shift in the phase, given like this. Okay, so P performs a useful logical operation. On a dual rail representation. Okay, so when I apply P, P applied to dual rail representation, I'll have this C1, 1, 0. This is important because it's relating like the free space to the medium, right? And the medium and free space. So this would be give me something like C0 exponential I eta 0, sorry, eta L omega C0 1 plus C1 exponential I eta minus eta 0 L omega C0 1, 0. And this is because, let's check this. P applied to the state 1, 0, just to remember this notation, it included like the tensorial product, right? It's this. So P applied to 1, we know that we have a shift in the phase. Let us give n 0 L omega C0. And P applied to 1 gives the shift. That is a shift like this. But P applied to 0 do nothing. So this is just. And in the other case, P applied to 0, 1 is P applied to 0, 1. But P applied to 0 do nothing. So we will have basically P comes here and applied to this term. Okay? Because applied to 0 is nothing. So it appears here I, but the difference is here, the exponential. C0, 0, 1. Because here we first was applied in the one single state and then in the zero state. So we have this difference, the shift. And here was the opposite, the zero state and one. So the shift is this way. Okay? It's eta 0 minus eta here is eta minus eta 0. So placing a phase shifter in one mode retards its phase. Evolution with respect to another mode. Okay? Traveling, of course, the same distance L in both cases. Okay, so we could arrange this in the following. So P applied to this plus C110. Okay. This will give me something like exponential. Let's call this all this theta. I'll use in the notation the Nielsen-Schwenk notation. So theta 0 I 0 1 plus C0 plus exponential I theta C1 10. Okay, this minus here, because this minus. Define theta in this way, so we change this why I have a minus. Okay, but in the book he also do something else, but I think it's not necessary. That's just redefine. There's a problem here. It's heavy today. So he redefined Nielsen-Schwenk book to do quantum computation. And relate this with the things that we already know, like rotations, gates. So it's convenient to redefine delta over 2. Because we could relate P, the operator, phase shifter, the phase shifter operator, P with the rotation operator. I'm using the Nielsen-Schwank book equation. What's this low today? I don't know if this is the computer. Okay. Equation is 4.6. That is this one. This Nielsen-Schwank book, okay? Rotation Z is given in terms exponential minus I theta Z, the gate Pauli Z gate, over 2. And just because of this over 2 here, it defined to have an over 2 here to make this relation. So P applied to C001 plus C110. Instead of write this way, I will write this way with this redefinition of theta. This is minus I theta over 2, 0, C0 plus exponential I theta over 2 C1, 10. And then I can make this relation here. This guy here with this guy. So P is related with the rotation in the Z direction, Z of theta. So I could write this exponential minus I delta Z over 2. Okay? And we can check this. This is in the dual radial representation. So if we are defining this, remember, let's see if this definition works. So this, to make the thing simple, this 0, 1 is the, we define as the zero logic. And 1, 0 we define with the 1 logic. So just to remember, R Z of theta is something exponential minus I Z theta over 2. That will give me these matrices. 0, 0 exponential I theta over 2. Okay? just using the rotation Z gate. So if we apply this to the zero logic, make this multiplication, where the zero logic is matrix form is 1, 0, right? And if you make this multiplication, we'll see that this is exponential minus I delta over 2 multiplied I0. In other words, is minus I theta over 2 is in the zero logic, but the zero logic is 0, 1. Exponential minus I theta over 2 0. That give me this part apart the constant C0. Okay, and we can check RZ of delta applied to 1L, 1 logic, the same, minus I delta over 2, 0, 0, exponential I delta over 2. 1 logic is just 0, 1, and this will give me just this table. Theta over 2, 0, 1. And this is exponential I theta over 2 with the 1 logic, which is I theta over 2. 1 logic is the state 1, 0. That's the same as we found before, without use the rotation. It's the same expression. So P, we could redefine a Hamiltonian for P. 1 we can think of P as a resulting from time evolution under the Hamiltonian. This Hamiltonian. H eta 0 minus eta Z, where Z is the Pauli gate, right? Pauli Z gate. This is equation 722. So with this Hamiltonian, P is exponential minus AH LC0. With this H. So a phase shifter is equivalent, we could say, like a rotation in the Z direction, right? In this representation, in this dual rail representation. And okay, I will leave some homeworks. Homeworks will be exercise 7.6, 7.7, and 7.8. Okay, the Newton frame. Okay, I think this is enough for today. And in the next you will see like quantum properties, something we do something similar, looking for the best Hamiltonian to represent beam splitters. Okay, questions? Okay, I have here Bombardier just wrote that he have a new course announcement to make. And those who can stay, please wait until the end. So, okay, Bombardier.
Yes, indeed, I am back. Maybe you can stop sharing so I can share.
Yeah.
Thank
Okay,
you.
so we finish for today.
Okay, so actually, can I ask if Dimitri is here? No, he's not in today. It's okay. Let's see. Let me share. I'll be brief. Okay, so in partnership with Dimitri and a group, he's a quantum meetup group, or actually I think two groups. One is to do with the physics called Physics with Friends, or Friends, if I'm not mistaken. And the other one is just, I think, Quantum Computing Meetup, which is a group Dimitri created. I think it's based in California, in the West Coast. So we are going to be partnering with them to do a course on representation theory. Most of the course, all this will be done by one of their community members, Wayne Dam, and you are welcome to join. The only caveat is, I think, if I'm not mistaken, this will be held in West Coast time. I'm not sure yet what time. I will confirm with him just to be sure. But yeah, everyone else who are interested in representation theory, you are welcome to attend. Actually, in our group theory course, the one that I did, I think last year, or towards the end of the 2022 or something, we did cover a little bit of representation theory. Okay, but this course here will be pretty much focused on the application side as well. So it will be heavily focused on the application. In fact, let me show you. After you go through the basics, you will see the applications in chemistry, in physics, and also application, especially those of you who are interested in machine learning stuff, application in machine learning. So yeah, it's a great opportunity for those of you who want to attend the course. We'll also have a section on the application side on quantum, in particular things to do with the equivariant embeddings. Max, I think you all remember Max, one of the mathematicians. He will be giving some sessions on embeddings, in particular through the use of unitary representations. So yeah, so that's all I wanted to say. I will be sending out an announcement over the next couple hours or so, once I confirm the time with him. And then, yeah, people can register to attend. Unfortunately, he is not keen into recording it, which is fine. So, those of you who want to take this course, you will have to, attend the live sessions. I think the rationale behind it is because recording might put off some people from participating. He wants the course to be very, to be very interactive, even for those who know nothing or little about group theory. Yeah, so, but the part with the Max on unitary representations and their application to quantum embeddings will be recorded. Yeah, but that will be at the end of the course. So if you know something about representation theory, whether you attend this the other sections, the basic introduction through this course, or maybe you watch some of my introduction to representation theory in our playlist, you should be able to follow Max when it comes to his part of the course, which we will record. That's it. Any questions? Any comments?
Cover regroups or just representation theory in general, like finite groups.
Yeah, just the representation in general and finite group. I know I promised one one course on, actually there will be one, I promise you guys, at some point, on Lie groups, Lie algebras, and their representation. So this is actually an opportunity for those of you who can to get the basics of representation theory, because then when we start to deal with the groups like Lie groups, then things become easier. Well, technically, in the Maxis part of the course, because you'll focus on unitary groups, these are Lie groups actually. So, in a thing, without mentioning Lie, you will be actually, you will come across SUN, these groups that are actually Lie groups, prototypes of Lie groups. So, in Maxis section of this course, you will get exposed to Lie groups in a without Lie groups without saying it's a Lie group. So, but you will have to wait until we actually have a more dedicated course on Lie groups and Lie algebras, as a matter of fact, plus the representation, to actually get into it. Yeah. And we will probably have some review. I don't know how many people remembers what a smooth manifold is. So we'll probably have a review on differential geometry a little bit, covering manifolds and these things, without going through all this stuff that we won't probably start from, like, we'll assume people know what topological spaces are. So we can start from manifolds to make it easier. Any comments? Okay, I'll stop sharing, and maybe Carlos, I hand over to you. Sorry for crashing your session.
No problem. It's good to know how the course is coming. I think it's helpful, always helpful. The things are, in some sense, linked. Yeah, okay. So, questions for today lecture? Otherwise, I will stop recording so don't be so. The video don't be so big.
Yeah, maybe we can stop recording to make if people feel more comfortable to participate, and then if not, we just end.
Okay, so bye, people from YouTube. Till next Friday. We will talk about link splitters.